Today we're going to talk about the different models of the atoms, and then how also the history behind the different models of the atoms. So first, way back in the day, on the original thoughts, Greek philosopher Aristotle classified the fundamental elements as fire, air, earth, and water. Those were the things that made up everything in the universe, so our fundamental elements. The ancient Chinese believed that the five basic components of the physical universe were earth, wood, metal, fire, and water. So similar idea here. Those were the main five things that composed up everything else in the earth. In India, 3rd century AD, the five gross elements were claimed to be space, air, fire, water, and earth. So you can see a certain trend here between what they think make up everything else, those fundamental elements that were first originated and created. Democritus was a Greek philosopher in 400 BC. He was the first to suggest the existence of atoms. And then he made the definition for atoms was the smallest particle of an element that retains its identity, which is what we use for the definition today. He could not support his idea or answer the question what holds everything together, so his concept was actually dismissed. He was way ahead of his time and known for his first coining of the term atom. You can see his model on the far bottom right, just a round solid ball. But he did know that those were the things, atoms were the things that made up everything else. Way later, John Dalton came along, and he was an English chemist in the early 1800s and created Dalton's atomic theory. In Dalton's atomic theory, he said that all elements are composed of tiny, indivisible particles called atoms, and atoms of the same element are identical. The atoms of one element are different than the atoms of other elements. This gray one here might be a carbon atom. This yellow one might be my lithium atom, might be my hydrogen and helium, and maybe my nitrogen atoms. So the atoms of one element are the same, but the same element are identical atoms, but different elements have different looking atoms. Atoms of different elements can physically mix or chemically combine in whole number ratios and form compounds, and he also stated that chemical reactions occur when these atoms are separated, joined, or rearranged. So Dalton's model of the atom is just a bunch of different shapes of the atoms to show the different types or different sizes and colors of the different elements. So Dalton was also known for his research in color blindness, and he wrote a book about English grammar. So he was a very smart guy, not just in the chemistry area, but in English and in genetics as well. Next we have Eugene Goldstein. We credit him for discovering the proton. He was a German physicist, and in 1886 he discovered positive particles by observing Cornell rays in a cathode ray tube filled with hydrogen gas. If you ever get a chance to watch a video on cathode ray tubes, that is a good idea to get an idea of how they work. But pretty much you have an anode side that is positively charged and a cathode side that is negatively charged. The cathode in this diagram has the holes in it. What happened when he put hydrogen gas inside of this cathode ray tube? What he could see was he could see these positive particles coming towards the negative end. Because remember, opposites attract. So these positive particles are going towards our negative side. He couldn't see the negative ones going towards the anode because that wasn't visible, but he did notice the positive particles moving towards his negative side in his cathode ray tube, and so he did discover positively charged particles. He didn't name it the proton yet, but we do know that the positively charged particle is our proton, and it's present in all of our atoms. Next we have J.J. Thomson. He discovered our electron using a similar experiment in 1897, so still using that cathode ray tube experiment, but instead of looking at just the positive side, the particles that move towards the negative side, negative pole, he looked at the positive pole and could see that there were negative element or particles that were being emitted at that side, and that these particles must have had a negative charge if they were going towards the positive pole. His experiments demonstrated the presence of the electrons. He did these multiple times. So what he discovered then was that there's negatively charged electrons in an atom that were floating or moving in a sea of positive charge. So his model we call the plum pudding model that he established in 1904. You can see in the bottom right his plum pudding model. How do you want to remember that somehow? Maybe J.J. Thomson likes his plum pudding, or Thomson likes plum pudding, J.J. likes plum pudding. Something to help you remember that. But pretty much it just looks like we have a sea of positive particles and a bunch of little negative plums plopped inside of that pudding of positivity. We have Ernest Rutherford next. He was a New Zealand-born British chemist and physicist. In 1911, he discovered the nucleus and concluded that it contained a positive particle, which then he named the proton. So we already know that Goldstein found the positive particle. He realized that there were positive particles in the atom, but he didn't name them. Rutherford named them the proton, and Rutherford also discovered that they were only in the nucleus. There were no positively charged particles floating around anywhere else. So what he did, if you can see in the bottom left picture, he has an alpha particle emitter, shining those alpha particles through a piece of gold foil. What he noticed was that they were either diffracted off or some bounced back, and some passed through with ease. So because of that experiment, he realized that there must be something in the center of the nucleus, or in the center of that atom, that tells me that that because of the bouncing back and bouncing off and scattering off. So the first splitting of the atom using nitrogen alpha particles, he discovered the protons. Ernest Rutherford is known as the father of nuclear physics. He also discovered half-life. But the main thing you want to remember his contribution to science is his gold foil experiment finding the nucleus. And what he found here was that using the cathode, or using the alpha particle emitter, shining those alpha particles into a piece of gold foil, some alpha particles bounced back, some went through because they must not have hit that nucleus, and then he discovered that there was a positive particle in the nucleus, and that is the proton. So the main thing to remember about Rutherford is he discovered the nucleus and named the proton. Moving past Rutherford, we have now Niels Bohr model and de Broglie model. Bohr's is kind of the planetary model of the atom. They have defined paths for the electrons. That's probably the one that you memorized and learned in middle school. Bohr was a Danish chemist and created the particle theory in 1911. He said electrons travel in circular orbits called energy levels with quantized energy. He also looked at the line spectra to discover this, which we will talk about in our next unit. So Bohr's model looks like a planet's revolving around the sun. That's why it's kind of called a planetary model. We also have de Broglie. He was a French chemist, and he came up with the wave theory in 1924. So building off of Bohr's model, similar, but he said electrons don't exactly follow this planetary orbit. They kind of act as waves, not particles. So they have a dual nature to both particles and waves. They want to act as both, so we kind of have this wave theory going for our model of the atom for de Broglie. Some important vocabulary. Energy level is a fixed energy of an electron. So in this picture here, n equals 1 would be the first energy level, n equals 2 is the second energy level, and n equals 3 is the third energy level. Quantum is the amount of energy required to move from one energy level to the next. So if I was going from n equals 2 to n equals 3, it would be a specific amount of energy I'd need. If I was dropping back down, I would give off energy, and there's a certain amount of energy that I would drop. Moving up takes more energy, because if you think of it in stairs, it takes more energy to climb stairs than it does to fall down. You actually give off energy when they move down energy levels. Electrons don't want to stay at this higher energy state because that's unstable. Electrons would rather be at the lowest energy level that they can, but that is for our next unit. We have our electron cloud model, Schrödinger and Heisenberg. So we have Schrödinger is an Austrian physicist in 1887 to 1961. He is the father of quantum mechanics. He used mathematical equations to describe the location of the electron. So all these little red dots on here, kind of like pointillism, that's describing where those location of the electrons are, or the probability of finding an electron is higher at places of thicker red than of lighter red. So what Schrödinger did is he took the Bohr model, where you have energy levels and specific planetary orbits, and took it one step further, and he used math to find the likelihood of finding an electron in a specific certain position. What Heisenberg did was he was followed in about right after Schrödinger, said, I don't really think you can find the exact location because you can't know the precise location and the momentum, or how fast it is moving, of a particle at the exact same time. So you might either know where it is or how fast it's going, but you don't know both. So you're not really going to be able to find an electron. He also said electrons don't move in defined orbits, but rather they're just kind of floating around in a cloud. And in 1932, he got the Nobel Prize in Physics for the creation of quantum mechanics. So even though Schrödinger is the father of quantum mechanics, Heisenberg was kind of the one that took Schrödinger's findings and created quantum mechanics. Our last person is Chadwick. He was an English physicist. He doesn't have a model of the atom, but we do credit him for finding our neutron. In 1932, he tracked particle emission from radioactive elements, which are pretty much every element past atomic number 82 has some radioactive isotope of its or form of radioactiveness. And he noticed that there was a particle that had no charge that didn't go towards either the positive or negative part of the cathode ray tube. That explained why our atomic mass and atomic number are different, or almost double. Our atomic mass is almost double our atomic number, but not always. What he did was he realized that when he took beryllium and bombarded it with positively charged particles, alpha particles, a beam of high penetrating power was created, and that high penetrating power beam then could go through paraffin and didn't care. It's not deflected by the electric or magnetic fields, so it had to be neutral because it didn't care about positive or negative sides. So he realized then that there was a particle in there that had no charge, named it the neutron. So here's one last look at all of your main models and the growing of our models from just a brown solid ball all the way up to our current electron cloud model that we have the most recent of.